What's up, all my reactive and somewhat volatile chemistry students? Mr. McCarson back again with another video. This time we're starting a brand new unit on atomic structure. And this video lecture is going to focus on the history of atomic theory. This is part one, and we're going to go all the way back in time to the ancient Greek civilization. We're going to take a look at Democritus and his ideas. We're going to talk about how those played a role in the evolution of the and development of the subject of chemistry, the science of chemistry, all the way through John Dalton and his very famous atomic theory. So thank you for being here. I hope you enjoy the lecture, and let's get down to business. All right, so first take a look at this wonderful gentleman right here. This is the very famous Democritus. He was a Greek philosopher. Now, very important distinction. Philosophers were not scientists by our modern definition. They observed the world around them using their senses, but what separated them from modern science was that they didn't rely on collecting data from experimentation and present that data as evidence for their ideas on how the natural world worked. And anyways, Democritus is said to have lived from around 460 BCE up until 370 BCE. And today we give him credit for the original idea of the atom. And to the best of our abilities, we think that would have happened and occurred around the year 400 BCE. And once again, these dates are speculative. There are no official writings that have survived from the time of Democritus. What we know about him was actually recorded from rivals of his ideas, such as the famous Aristotle. We'll talk about him shortly. Okay, so Democritus is said to have gotten the atom through a very cool story, which we'll share on the next slide. Okay, so as the story goes, Democritus was walking along the beach with his teacher and mentor, a person by the name of Leucippus, another Greek philosopher. Okay, and Democritus was bending over and grabbing a grain of sand. He grabbed a handful of sand, and he turned to Leucippus and he posed a question. He said, "If we take a grain of sand and we cut it in half, and we take one of those halves and we cut it in half again, and we keep repeating this process over and over, what is the smallest piece of a grain of sand that's possible to produce? Does there come a point where we can no longer take a unit of sand and split it in half?" And he famously, in the Greek language, we derive this term, okay, and it's the modern day root of the word atom, and he came up with the term atomos, which is a Greek word meaning indivisible. Okay, so Democritus, when we say the term atoms, that goes all the way back to Democritus talking with Leucippus on the beach and posing the idea that there is a smallest unit of matter. Okay, there's a smallest piece of all things that make up the world, and those smallest pieces he thought, or he called, atomos, or indivisible particles. Okay, now I want to draw your attention to this painting. This is a really cool painting by Francois Andre Vincent, and it's called Democritus Among the Abderitans from the year 1790. And this is really cool because this is actually a painting you can go see here in Los Angeles. It's at the Los Angeles County Museum of Arts, what we call in shorthand the LACMA. And if you've never been to the LACMA, it's an awesome day out. Highly recommended. Take your family, take your friends, take your significant other. You'll really enjoy your time there. Make sure you get a full day. There's a lot to see, many famous artists, and you can go and spend a little bit of time with your favorite Greek philosopher, Democritus. Okay, so you might be asking yourself, well, Mr. M, 400 BCE, Democritus came up with the idea of the atom and atomos, something that is so small it becomes indivisible, which make up the foundation of everything that we see in the air, the oceans, the solid materials that make up the earth, what we use to build our civilizations out of. So, why didn't we start learning about the atomic theory at the time of Democritus? Well, there was another Greek that came along. And this Greek philosopher was very famous and very powerful, and unfortunately, his ideas were very wrong. Okay? So enter Aristotle, a famous philosopher. Now, he would have been very young when Democritus was old. So, kind of by our closest historical record, he would have been about 14 or 15 when Democritus passed away. Once again, the dates of Democritus's death are not perfect, but he would have been exposed to Democritus's ideas on atoms. They call it atomism, right? Democritus and Leucippus's ideas on atomism. Now remember, in the time of the Greek philosophers, nobody did experiments. They simply observed with their senses and tried to come up with ideas, but they weren't really hypotheses because they didn't test them, right? Now, Aristotle had a lot of great stuff that he did. He had a lot of wonderful writings. Student of Plato, he had a very large academic institution, very important in terms of what he contributed to the world, what would eventually become biology and anatomy and understanding um, life forms. So, very good on those fronts, but terrible when it came to chemistry. So, the problem was that Aristotle's idea was that all substances were made from only four elements. And you've probably heard this before. It is the foundation of what we know as the Pokemon battle system. He felt that everything was fire to represent hot, air to represent light, earth to represent things that were cool and heavy, and water to represent wet. And that you could make any substance on earth or in the heavens if you blend these elements in different proportions. That's how you got all substances. So if you wanted something like a metal, right, you would take fire and earth and blend them together to get something that's hot and molten, and then hit it with water to solidify it. And so it really was a very kind of oversimplistic idea, but this was Aristotle's idea on substances and the elements. So the idea of the elements arose among the Greeks, but those in Aristotle's school of thought and philosophy felt there were only four. Okay, now thankfully we expanded this out in Pokemon to contain many more than just four elements, which gives us our robust battle system we know today. But in the time of the ancient Greeks, it was air, earth, water, and fire. Okay? So, who is right in this battle of ideas? On one hand, we had Democritus and Leucippus with the idea of atomism and atomos, that substances did have smallest individual units that could no longer be broken down, called atoms. And then we had Aristotle, who felt that all substances were a blend of earth, air, water, and fire in different proportions to make everything. And Aristotle thought that things could be divided infinitely. Like you could keep making water smaller and smaller and smaller and smaller. He felt that the human eye couldn't detect it anymore, but that it was possible to split things in half essentially forever. Okay? Now, remember, the Greeks did not experiment. They settled disagreements by arguments. Okay? So Aristotle was a better debater, right? He had the ability to get up there and stream, if you will, for his time. He was a very popular streamer. And he won because he was able to argue his ideas more effectively versus Democritus's ideas. Now, remember, Democritus at this time was very old, and when Aristotle was really grinding, he was dead. So it was kind of an unfair fight because Democritus wouldn't have been really in his prime to argue his ideas. And because there was no evidence, his ideas, Aristotle's ideas, ended up carrying all the way to the Middle Ages in Western civilization. Now remember, this story is focused on Western civilization. There were other really cool things happening in places in Asia and Africa and North America and South America. Um, we're focusing on kind of the historical textbook Western civilization development of the history of atomic theory, but we will take some time to explore what was happening in different cultures and civilizations around the world when it came to the elements. Okay? Now, Aristotle's ideas, especially in Europe, the Mediterranean region of Earth, they carried all the way until the Middle Ages, until the rise of alchemists, when they had the goal of turning lead into gold in Europe. And this is really when the story would start to turn. And we'll talk more about the early alchemists on the next slide. Okay, so we're going to fast forward here about 16 to 1700 years. So, after the time of Aristotle, what occurred was that the majority of European society, and once again, we are kind of focusing this story, the textbook focuses on looking at the rise of chemistry from a European or Western perspective. It doesn't necessarily take into, and it doesn't mean that there wasn't amazing things going on in areas like North America, South America, Africa, and Asia. Different parts of the world were doing all kinds of incredible things, and we'll talk about those in a special segment. But in Europe specifically, in the Mediterranean region and parts of the Arabic Peninsula, what happened was we got really fixated with Aristotle's idea of the four elements. So in Europe, they specifically lasted for about 17 to 1800 years. Like it was a really long time that we were stuck on this. A lot of it was because of their simplicity and how the idea of the four elements really fit into the um, major institutions that controlled Europe. If you think on your history, we had the rise of the Holy Roman Empire, we had the rise of Lutheranism. Many of the nobles that controlled different regions were very, very religiously motivated, and so Earth, Wind, Water, and Fire kind of fell into a natural step with the ideas in many religious texts of that time. And so, anyways, to actually think that there were other elements or forces going on outside the power of God or whatever God was in their religious text was considered blasphemy in Europe. And so the first major step away from Aristotle's ideas of earth, wind, water, and fire came with the rise of alchemists, who, to be clear, were not scientists because they did not share or openly write about their ideas in a way that fostered knowledge in a community. And then a lot of their motivation was greed. Like in science, your motivation shouldn't be pure greed. Yes, there are people that invent and discover things from an entrepreneurial aspect, and that's cool, that's great, that will can help make you a lot of money, but that's not really the spirit of science and of learning and the free sharing of information. Now, Paracelsus was the first to break this mold. He was a Swiss alchemist and physician who lived and worked in the early 1500s. And then all the way up from Paracelsus through the great Antoine Lavoisier, who famously considered is the founder or the father of modern chemistry. Many advancements were made. This was a solid approximately 300 years of incredible growth and official development of the science of chemistry. Now, it all kind of culminated with the official destruction of like Aristotle's ideas of the four elements, came with a scientist named John Dalton, who was a professor in England in 1808. And what Dalton did was he summarized many different scientists who worked close to his own lifetime or in the 100 to 200 years before him, like from Paracelsus up to Lavoisier. He summarized the results of their experiments in what we call Dalton's atomic theory, which are 5 rules that officially describe what atoms do. So Democritus had the idea of the atom. And then Aristotle, because he was so influential and a great debater, kind of overpowered it. And the idea of the atom was lost for thousands of years until the alchemists and then a number of different chemists working on very, very influential experiments in the history of this subject culminated in Dalton writing down an official set of rules for what atoms did and how they behaved. And we're going to learn about those 5 set of rules in Dalton's atomic theory. So, just going through a couple of the major experiments and advancements in the subject of chemistry after Paracelsus. One of the first ones we have was Hennig Brand, and Hennig Brand was the first to use chemistry to isolate and discover a new element. He discovered phosphorus, and kind of famously, he did this by chemically decomposing his own urine. So he was trying to find gold because that's what the old timers did. And he believed that gold was naturally found in our urine. Why? Because our urine's gold. And it's not so crazy if you lived a couple hundred years ago to think that when we didn't really know what atoms were. And so he famously distilled urine, he boiled urine, and he isolated what was left over, and he found when he superheated the leftover paste, he actually was able to chemically extract the element phosphorus, which is very flammable. It ignites in the air. That was really an influential step into the rise of chemistry. So Hennig Brand, discovery of phosphorus. Next, we have Robert Boyle, who was a British physicist and chemist, and he's famous for, among a lot of things, Boyle did a lot. So he was in the Royal Institution in England. Really important because he's considered to have the first official textbook on chemistry, and it's called The Skeptical Chemist. I love the name. He's also famous for gas laws. So we're going to learn Boyle's law later this year when we talk about the nature of how gases behave. So we have Robert Boyle there in the middle. And then next we have Henry Cavendish. Cavendish discovered hydrogen by mixing the metal zinc with hydrochloric acid. And he was actually isolating it. He realized that he could light it on fire, it would combust, even though they were still not really certain what heat and thermal energy. They rarely at that time they thought of heat as its own element with the name phlogiston, and so it took a while. And Antoine Lavoisier had to do work to overcome the idea of phlogiston, but Henry Cavendish, very famous for the discovery of hydrogen and the development of many chemistry lab techniques. Okay, so continuing our list of famous chemists in this early era of the pioneering mavericks of the subject. Next, we have Joseph Priestley, and he was a clergy member in England that was famous for working in breweries. So he would go and work in breweries, and he discovered carbon dioxide gas would come out. It was very heavy, and it would actually put out matches. It would actually smother flames. But Priestley's very famous because he started doing experiments which would lead to the discovery of oxygen. Now, depending on the text that you look at, he didn't get credit for it. Lavoisier was very aggressive and named and officially claimed discovery of oxygen. But make no mistake, without Priestley, Lavoisier wouldn't have been able to do that. And the fun thing was this was kind of one of the first major rivalries between chemists. Priestley and Lavoisier were very competitive. So they were both working on similar projects and going back and forth, and they would talk to each other. But ultimately, Lavoisier would get a lot more credit than Priestley, probably unfairly. Not to discredit either, they were both brilliant scientists in their own ways. Um, Priestley was much more humble. He came from meager beginnings. He wasn't born into a high level of nobility or wealth, while Lavoisier was. Lavoisier was a tax collector for King Louis, and when you go through the French Revolution as a tax collector for King Louis, bad things are probably going to happen to you. So from Priestley, we move on to Antoine Lavoisier. This is a painting of Lavoisier with his wife, Mrs. Lavoisier. And Lavoisier did so much. He worked on things like the law of conservation of mass, combustion. He did experiments to disprove the concept of phlogiston, that heat wasn't an element, it was an energy. He worked on the law of definite proportions. He discovered a number of elements sometimes through nefarious methods, sometimes through original work. And so Lavoisier did so much. Unfortunately, at the start of the French Revolution, Lavoisier was not in good graces with the people that overthrew King Louis, and they actually took and beheaded Antoine Lavoisier. So one of the greatest minds we've ever had in chemistry didn't really live a full life, and we don't know what he could have done with more years. Because of the French Revolution, he was actually taken to the guillotine, and so Lavoisier didn't live long enough to really uh, have a full life of chemistry to do. But what he did discover in his life was very, very ground changing. And once again, to use kind of the old fashioned patriarchal term, um, he is kind of given the moniker of the father of chemistry because of all of the discoveries he had and the work that he did to move forward. He was incredible because of how detailed he was. Now, to be clear, he had money for the best equipment in the world. Like his lab had some of the most precise and intricate tools of measurement and calculation that had ever been created. And that happened because of the wealth that he had. So why he was so influential was he really was ultra data driven. The calculations and measurements he took were very meticulous for the time. He kind of created a framework for collecting data and using the analysis of that data to come to conclusions and develop new theories on how the elements worked. Lastly, here's a picture of John Dalton. And Dalton was kind of a meta aggregator of all of these previous scientists we talked about. He looked at and studied all of their work, and he was a professor and a teacher at a university. And so he would actually take these ideas and present them to his students. And the more he did that, he started to come up with and develop a set of framework that he would roll into 5 rules that we call Dalton's atomic theory. And this was groundbreaking because up until this point, um, we were toying with the idea of atoms like Democritus did, but nobody ever really said it. Like nobody said, hey, all substances are made of the smallest piece of matter, which is called an atom. And Dalton was the first to do that. So, in 5 rules, which we'll go over here shortly, Dalton changed the world of chemistry and ultimately of humanity by giving scientists a set of rules to follow about what atoms do and how they behave. So, all 6 of these scientists are important to remember. Even though there are many more, there were lots of people working at this time. This is just a brief glimpse into a number of influential scientists that informed Dalton's atomic theory. Okay, so Dalton's atomic theory is based on 3 different rules that we discovered concerning elements. The first one is the law of definite proportions. Okay, and the law of definite proportions was based on experiments by Joseph Priestley and Antoine Lavoisier, but credit for the law, the way you see written here, was written by Proust in 1797. So Proust officially wrote this rule that you're about to read, the law of definite proportions, which reads, a chemical compound contains the same elements in exactly the same proportions by mass regardless of the size or source of the compound. Okay, so let's break that down. What does that mean? It means in a compound like water, there's a specific ratio of elements based on their mass. Okay, so it's a ratio by mass. Now, let's illustrate that in water. If it's got a formula of H2O and we look at the relative atomic masses, hydrogen had a mass of 1 in the late 1700s, and we knew oxygen was 8 times heavier, so it had a mass of 8. And so in water, what we knew is for every 1 gram of hydrogen, there was 8 grams of oxygen. So it had a ratio of a mass of 8 to 1. Okay? So here's a really nice slide to illustrate Proust's law of definite proportions. So if we have we'll just take a famous simple example we're familiar with, what we exhale and what helps keep our planet's temperature hopefully stable, carbon dioxide, the formula CO2. If you have 1 gram of CO2, the ratio of oxygen to carbon by mass is always going to be 72.7% oxygen and 27.3% carbon. So the mass of 1 gram of CO2, 72.7% oxygen. Now, if we bump that up to 16 grams of CO2, guess what the percent of mass of oxygen is in that overall substance? Same thing. As long as it's carbon dioxide, 72.7% will still be the mass of the oxygen, followed by 27.3% the mass of carbon. Now, if we switch the formula to something different, let's say we go from carbon dioxide to carbon monoxide, which is carbon bonded to a single oxygen, now our ratio is going to change, okay? So 1 gram of carbon monoxide is 57.1% the mass of oxygen to 42.9% the mass of carbon. So there is a fixed ratio between masses. And once again, we still didn't know directly about individual atoms, but this would lead to the fact that atoms form formulas and whole number ratios. But at the time, this was groundbreaking because every compound had a ratio of one element to another that no matter how much of the substance you have, as long as it's pure, you're going to get that same ratio or percentage over and over again. Okay, so the second law that was discovered around the time of Dalton, or was actually his own, and he gained this through insight from his own experiments and observing the experiments of other scientists. We call it the law of multiple proportions. Now, the law of multiple proportions states that if two or more different compounds are composed of the same two elements, like CO2 to CO, right? Those are different compounds. Carbon dioxide is different than carbon monoxide, okay? And they have different formulas. Now, then he said, then the ratio of the masses of the second element combined with a certain mass of the first element is always a ratio of whole numbers. What the heck does that mean? And John Dalton did this in the year 1808. Okay, so examples of formulas where you have the same elements but in different ratios would be like CH4 to C2H6, right? So we have methane and ethane. These are natural gases. And let's illustrate what we mean on the next slide, because this law is a little bit more difficult to understand than Proust's law of definite proportions. Okay, so many of you are probably feeling like Fry from Futurama with that last definition of multiple proportions. Like, what, what are you trying to say, Dalton? Let's break down the lyrics because it's all about the lyrics, ladies and gentlemen. So, in water, the formula is H2O. In water, for every 1 gram of hydrogen, there's 8 grams of oxygen. That's the ratio. Okay, so it's 1 to 8. Now, hydrogen peroxide is similar to water, but different. Hydrogen peroxide is H2O2, okay? So in hydrogen peroxide, there's 16 grams of oxygen per 1 gram of hydrogen. Now, if we compare 8 grams of oxygen from water to 16 grams of oxygen from hydrogen peroxide, it's a 2 to 1 ratio, okay? Which is a ratio of whole numbers. Now, what this means, let's like, what the heck does that mean and why is it important for me to know on a test? It means that you can only add, if you break that down all the way, you can only add atoms in a compound in whole numbers. You can never add half an atom to create a different compound. Atoms must combine in whole number ratios. That's what the law of multiple proportions allows us to come to the conclusion of, okay? So it's important because it meant that compounds always form using whole number ratios, which is why that big old long convoluted definition matters. Here's another nice graphic to illustrate the law of multiple proportions. This comes from sciencenotes.org. Thank you, Science Notes. So if we look at 1 gram of carbon, and we're looking at carbon monoxide versus carbon dioxide. If we're looking at carbon monoxide, for every 1 gram of carbon, there's 1.333 grams of oxygen atom. Okay? If we look at carbon dioxide, for every 1 gram of carbon, there's 2.666 grams of oxygen. So if we compare 1.333 to 2.666, we get a ratio of exactly 1 to 2, which means you're adding another whole atom of oxygen if you kind of break that down the way it was at the time. Very important. You can only add atoms to compounds in whole numbers. You can never add a portion or fraction of an atom. All right, the final of the 3 laws that was very influential in helping Dalton create the 5 parts of his atomic theory was the law of conservation of mass. And this was alluded to by the work of a number of scientists, including Henry Cavendish. But the main person that kind of historically gets credit for conservation of mass is Lavoisier, 1773. And he did really meticulous measurements of the mass of reactants. And what he found is if you carefully measure the mass of the reactants and you carefully control and measure the mass of the products in a chemical reaction, mass is neither created nor destroyed during normal chemical reactions or physical changes. That's important. So, like if you take a piece of paper and you rip it in half, the paper, the mass of the paper before you ripped it should equal the mass of the pieces of paper that you weigh at the end, right? That's a physical change. In a chemical reaction, let's say you take a piece of paper and you burn it. If you know the mass of the oxygen used in burning the paper and you know the mass of the paper, the mass of the products, the carbon dioxide, the water, and the ash should equal the paper and oxygen that you started with. Okay? So mass is neither destroyed nor created during ordinary chemical reactions or physical changes. And this would show up in Dalton's atomic theory. Here's a good graphic organizer and visual to help you understand conservation of mass. So remember, reactants are on the left side of our reaction arrow here. You know a chemical reaction if there's an arrow separating left from right. The left side are known as reactants, the starting substances or mixtures in a chemical reaction. And then the products are what we create after the chemical bonds have been broken or made or rearranged. Okay, so in this one, the reaction is 1 molecule of oxygen plus 2 molecules of hydrogen gas will produce 2 molecules of water, H2O. So the mass of the system is the same before and after the reactions. If you look, there's 2 atoms of oxygen in the reactants, and there's 2 atoms of oxygen in the products. They're bonded differently, but those same 2 atoms are represented. We start with 4 atoms of hydrogen as reactants, and we still have 4 atoms of hydrogen as products. They're just changed what they're bonded with and how they're bonded. So this is the fundamental basis for the law of conservation of mass, and it's a big deal. All right, so thanks for sticking with me this far. We're on our 16th slide in part 1, the history of the atom and atomic theory from the time of Democritus up through the time of Dalton. And here's Dalton's atomic theory. So let's go through all 5 parts. The first part of Dalton's atomic theory. Number 1, all matter is composed of extremely small particles called atoms. And at the time of Dalton, we believe that was it. The atom was as far as you could split an element and still retain its properties. And not any of the scientists at the time, at least those that were popular in the literature, believed that an atom could be subdivided any further, meaning there was no talk of protons, neutrons, or electrons. Number 2, atoms of a given element are identical in size, mass, and other properties. Atoms of different elements are different. So a gold atom was not the same as a silver atom. They were fundamentally different. They had different properties, different sizes, and different characteristics. and you could not change between those. Okay. Number 3, atoms cannot be subdivided, created, or destroyed. This is where the law of conservation of mass comes in. And once again, at this stage, no mention of protons, neutrons, or electrons. So subdividing an atom wouldn't be around for another almost 100 years. Number 4, atoms of different elements combine in whole number ratios to form compounds. This is where the law of definite proportions and multiple proportions comes into play. So, for example, water is always 2 hydrogens to 1 oxygen. You can never have it be 1 hydrogen to 1/2 an oxygen. That's mathematically not how compounds work. Always whole number ratios of atoms in a chemical formula. And then finally, in number 5, in chemical reactions, atoms are combined, separated, or rearranged, or some combination of those 3. And so these are what we know as Dalton's 5 laws of his atomic theory. And they're so important because they're the first time that a scientist said to the rest of the community of chemistry, here are the rules of atoms. These are what atoms do, and how they dictate substances and mixtures. So very important stuff. Now we're going to go ahead and wrap part 1 here. Thank you so much for joining me on this journey. I hope you enjoyed the story of the history of the atom. I love it, and I think it shows how amazing our growth of our collective human knowledge has been over thousands of years, and how little things like the debate between Aristotle's ideas and Democritus' ideas can change the course of thousands of years of human history. So I hope you enjoy. If you like this, don't forget to give it a thumbs up, and don't forget to subscribe to see upcoming videos. Thank you. Have a wonderful day. And as always, don't forget to study your chemistry. Bye. Have a good one.